Alright, in this video I want to talk about coordinate systems, Cartesian coordinates, parametric coordinates, and polar coordinates. I want to find the area of a circle with radius 3 and yeah, just talk about that a little bit and kind of go over it and shed some light on some of that information. So for starters, so briefly, what are polar coordinates and parametric coordinates and Cartesian coordinates? So it'll be easiest to illustrate that using Desmos. I really like their graphing calculator, and I don't know anybody that works for Desmos. It's not like I don't make any money off my channel anyway. I just happen to really like this free online graphing calculator. So I already wrote out all of the things, but the second one here, x squared plus y squared equals 3 squared, that is the Cartesian normal standard coordinates where the horizontal axis is x and the vertical axis is y. And in order to make a circle, you do x squared plus y squared equals r squared, but I'm going to be sticking with 3 for r for this video just to keep a little bit less, have a little bit less of the alphabet in the equations. So a lot of people like that. So x squared plus y squared equals 3 squared. It's a circle centered around the origin with radius of 3. If we were to use parametric coordinates, that's this third one here. And you'll notice, hopefully you can tell the difference between green and blue. See it changes a little when I hit green, but it still covers the same exact circle. That's because they're the same. The equations represent the same thing, but one of them is a parametric equation going from 0 to 2 pi. Technically there's a difference because it includes direction, but for visual purposes they're the same, they're equivalent. And let's see what else. So when you graph these, if you don't already know, graphing them, the reason it looks like a point where the x value is 3 cosine t and the y value is 3 sine of t, because in essence that's what it is. This format is showing you how to create every point. So you have t, which t is just a counter value. You would just, as you were graphing, you would just cycle through and count. And actually with parametric curves there is a direction implied, and the direction here is going from 0 to 2 pi. So we start with t equals 0, which, let's see, cosine of 0 is 1 and sine of 0 is 0. So this will give us the point 3, 1. So our starting point is right here, 3, 1, which I should be able to highlight. Yeah, 3, 1. And then, where's my finger? We move, oh, it's hard to keep it in the screen. We move around the circle counterclockwise, whether my finger was going the right direction in the video or not. So we move this way around the circle until we get all the way to 2 pi. The value, plugging in 2 pi for t gives us this last point. So that's how parametric equations work. The other thing, the third type, is polar coordinates. And to graph our circle in polar coordinates, you just say r equals 3. And you'll see that gives us the same area. When I switch between them, you can see the circle still covers the same exact plots, points in space. But for for polar coordinates, what's being represented is, so say we have a point, which this will actually probably, I guess you can't click on a point in polar coordinates like you can in Cartesian on this, in this calculator, but basically this point right here, to write this point, this would be the point. This will be easier to explain actually, going back and sketching it. So for polar coordinates, a point, like let's take, we'll take this point here, and let's imagine that that was 3 units this way and 0. So if it were the xy, in xy coordinates, this would be the point 3, 0, like we just had on the other screen. But to label this point in polar coordinates, you use the label r theta, where r represents the distance from the origin, so it's telling you to move 3 units from the origin, and then theta is telling you what angle to rotate in the counterclockwise direction from the x-axis. Yeah, and just say in the counterclockwise direction. So this point here, which I already drew, 3, 0, would be, actually this would also be 3, 0, because the radius is 3 and the angle in radians is 0. So in polar coordinates, this happens to be the same, represented in polar coordinates and Cartesian coordinates, but the numbers represent something different in each system. So let's take this point up here, which is 0, 3 in Cartesian coordinates, but in polar coordinates, the distance from the origin is still 3, and then our angle is pi over 2 radians. So that's this point in polar coordinates. So back to our equation for our circle is r equals 3, and the points that we're dealing with are r theta. So no matter what theta is, r is always 3. So that tells us that let's keep r at 3 and go through every possible value for theta. Oops, and pretend that's a circle. And technically it would keep looping over and over, but we don't usually care about that for what we're doing. So you'll see it just makes a circle with radius 3. So that's polar coordinates. And the other thing that I had on my little Desmos thing here was, so in Cartesian coordinates, the graph of the circle is x squared plus y squared equals 3 squared. But that presents a problem because when we do the integration, we want to have y equals something. We want to have an f of x because, it never wants to let me go back, because as you'll see, we're going to have a equals the integral from a to b of f of x dx. This is f of x or y, means the same thing, but we need to have, so our equation needs to be in the form y equals, so that whatever y equals, we can plug that in right here and take the integral of it. So when we look at this, so this right here, oh, those are like the same color. Let me just actually use one of these other ones because I had a different color already associated with them. That's kind of the same. Red stands out, kind of. Purple's a bad color, but so see the top half of the circle. So the square root of 9 minus x squared is the top half, and the bottom half would be minus. So top half, bottom half, top half, bottom half. When we do the integration, we're actually only going to need the top half, and I can actually explain why from this wonderful circle that's already drawn here. So if we take, the integral is going to be giving us the area under the curve. If we were just to take the top half of the circle and go from -3 to 3, because we're going to be going along the x-axis, which was shown because when I set it up, we have dx. We're taking the integral of f of x with respect to x, f of x dx. That means we're going to be moving along the x-axis, so we're going to want our lowest point on the x-axis to be the bottom bound, I think is the right word, and we want +3 to be the top value or the upper bound. And so, however, and if we just did that, if we took that, that will give us the top half. So alternatively, we can say area equals the integral from -3 to positive 3 of positive square root of 9 minus x squared dx. That'll give us the top half. Then we say plus, and then the bottom half. Plus, or we'll say plus the absolute value, because I think you might want minus, because I think this should give a negative area, so you would want either minus or plus the absolute value of the integral from negative 3 to 3 of, now we use the bottom half of the circle equation, so we'd have negative square root of 9 minus x squared dx. So that's the way to do it, where you use integration for every part of it. Another way would be that since we know that the top half equals the bottom half, we can just find the area of the top half and multiply it by 2. So we could set this up as, I'll write this in a second, but to avoid constantly switching screens, I'll just say it verbally for now. We could set this up as area equals the integral from negative 3 to positive 3 of, sorry, I meant to say 2 times. Area equals 2 times the integral from negative 3 to positive 3 of the square root of 9 minus x squared dx. That would give us the whole circle. Alternatively, another way is we can break it up here. I mean, you can break it up anywhere you want, but this is probably going to be the easiest place to break it up. So in this case, we would find the area of just this quarter of the pie, quarter of the circle. And since it is a quarter of the circle, which is honestly in this case pretty easily discerned visually, if we find this area and multiply it by 4, that will give us the area of the whole circle. So we can set this up, and the way we're going to set it up is area equals the integral from our lowest x value, which is 0, to our highest x value, which is 3, of square root of 9 minus x squared dx. So to show some of that again, yeah, actually I'll just erase all this graph stuff here. Where's my I was using this yellow. All right. So once again, I'll redraw that. It's going to be helpful to have a visual. And oh, that's looking a little better than a lot of my other circles did. Okay, so we're going to say, oh, and by the way, this is for Cartesian coordinates. Area equals integral from a to b of fx dx. This is for polar coordinates, which we're going to go over next. Area equals the integral from alpha to beta. You could have still called them a to b. They just called them alpha and beta to just avoid, to help make it easier to remember the distinction between the two, of g of t times the derivative of f of t dt. And this last one then will be in polar coordinates. The integral from a to b of 1/2 f of theta squared d theta. So back to our circle, we're just going to find the area of this portion and multiply it by 4. This goes from x equals 0 to x equals 3. So we're going to say integral, sorry, and we're going to multiply it all by 4. So we're going to say 4 times the integral from 0 to 3 of our f of x, as I just showed on the other screen, but I can work out down here, x squared plus y squared equals 9. 3 squared is 9. This is our formula that we're starting with. Solve for y, so we subtract both sides by x squared. Y squared equals 9 minus x squared. Square root of both sides, y equals plus or minus the square root of 9 minus x squared. But we are only concerned with the top half of the circle, which is just the positive value of the square root. So we're actually going to be using y equals square root of 9 minus x squared. This is our f of x. This is our f. Oops, that's not going to work. right over here. Okay, so now square root of 9. Actually, I'll just keep that as 3 squared. 3 squared minus x squared dx. Okay, so this is our formula. It's freezing up again. It did that to me earlier. So this is our formula. I didn't go over this. I wrote this up here earlier because this is what you might have memorized as a formula for the area of a circle. Area equals pi r squared. And since for all of these illustrations right now, I'm going to have set r equal to 3. 3 squared is 9. So 9 pi is our area for our circle. We can use that to check the integration process. This sine squared theta plus cosine squared theta is actually what we're going to use right now to solve this particular integral. You cannot solve this integral by u substitution. You cannot solve it by integration by parts. You can solve this integral by trig substitution. So if we have, typically when you learn this and memorize this, you have the square root of a squared minus x squared. If you see that for your f of x, you can use the trig substitution that x equals a sine of theta. And when you work out the process, that will allow you to integrate this to solve this. So in this case, for our actual integral that we have, we're going to say x equals 3 sine of theta because a equals 3. And then dx equals 3 cosine of theta d theta. So we're going to substitute that in, and we're also going to recalculate our bounds. So I'll start to rewrite this. So area equals 4 times the integral from something to something, we don't know yet because those are our bounds that we're going to change, of the square root of 3 squared minus, and then for x we substitute in 3 cosine of theta, and then that's squared. For dx we substitute in 3 cosine of theta d theta. Now our new bounds that we're going to do, so we can look at the picture visually. This is our area that we are calculating for. And if we are dealing with x as our variable, we're going from this x of 0 to this x of 3. But we're not dealing with x's now. For this second integral, for after I changed it, we're dealing with thetas. So in thetas, we're dealing with, this is where you start when you're dealing with radians, which is always what you're going to deal with for this type of problem. We're dealing in radians, and you go from here. This is our first value for theta, our lowest value for theta of 0. And we're moving in this direction, and our highest value of theta is here. And this value of theta is pi over 2. This one is pi, which we're not making it that far. And this one is 3 pi over 2, or 3 pi over 2, and 2 pi. The farthest we make it in theta is pi over 2. So for our new bounds, we're going from 0 to pi over 2. Now, the next thing we're going to want to do, say area equals 4 times integral from 0 to pi over 2 square root of, we're going to want to pull out that, I'm going to try to skip a little steps because this gets really long if you do every single step on a new line. So we're going to take 3 cosine theta squared will give us 3 squared times cosine squared theta. So that would give us 3 squared minus 3 squared cosine squared theta. We can factor out 3 squared. So I'll do that right now. So we'll be left with 3 squared times, what do you multiply, what value do you have to multiply by to get 3 squared? 3 squared times 1 equals 3 squared. Minus, what value do you have to multiply 3 squared by to get 3 squared cosine squared theta? Just cosine squared theta. Hope that made sense. It'd have been more clear writing it out, but it really adds to the time of the video. So then we have 3 cosine of theta, we didn't touch that yet, and we have d theta, we didn't touch that yet. Now, we can take the square root of this, because this is two things multiplied by each other. So you can break them up into two separate square roots, and this multiplied by each other. The square root of 3 squared is 3. We're going to bring that to the outside. This 3 sitting here with that's just multiplied by things with theta, not added or subtracted or some other kind of a operation. It's just multiplication. So we're going to bring this one also to the outside. So this one, as I said, turns into a 3. 3 times 3 is 9. 9 times 3 is 36. So we're going to get area equals 36 times the integral from 0 pi over 2. And what's left inside the square root then is 1 minus cosine squared theta. That's why this is written here. Cosine squared theta plus sine squared theta plus cosine squared theta equals 1. This is just something to memorize. And it's apparent from this that if we subtract the cosine theta, we get sine squared theta equals 1 minus cosine squared theta, or 1 minus cosine squared theta equals sine squared theta. So we're going to put that inside here. Sine squared theta. And we're still left with cosine of theta on the outside and d theta. So now, is that? Sorry, I have to go back several steps. I do this a lot in my videos, but I'm not re-recording the whole video. As you can see, x was supposed to be 3 sine of theta, so this was supposed to be sine of theta. This then was supposed to be sine of theta. And the same thing still applies, that this 1 minus sine squared theta equals cosine squared theta. So, oops, I don't want those ones to go. I'll just scribble it here. So this is actually supposed to be cosine squared theta. Sorry for the confusion. So, hopefully that didn't make the video too confusing. Yeah, so now when we take the square root of cosine squared theta, we're going to get cosine of theta. Cosine of theta times cosine of theta is cosine squared of theta. So area equals 36 times the integral from 0 to pi over 2 cosine squared theta d theta. Oops. And now we actually are going to want to do some trig substitution again in order to integrate this. And the substitution that we want to use is, because we have to reduce this power, so when you have to reduce the power, the substitution to use is cosine squared theta equals 1/2 1 should be plus sine squared theta. No, cosine squared theta, sorry. Cosine squared theta. Yeah, that's looking better. So now, if you had sine squared theta, which we don't need, but just to show you the other one that you would want to memorize is sine squared theta equals 1/2 1 minus cosine squared theta, which is where I was trying to make sure I had the plus and the minus correct, but it should be that the plus goes with cosine is the same, kind of how I remember. So this is what we're going to use. Sorry, made a mistake again. I'm doing all this from memory. So this is actually supposed to be cosine of 2 theta. That's the whole point for using it, is to reduce the power. And this is the same, but it should be cosine of 2 theta. Okay, anyway, so this is what we're using. So area equals 36 times the integral from 0 to pi over 2 of 1/2 times 1 plus cosine 2 theta d theta. And now we can pull that 1/2 to the outside. So we'll have area equals 18 times the integral from 0 pi over 2 of, I'm also going to split this up. So this would be just 1 plus cosine of 2 theta, but we can split it up into this thing times the integral of the 1 plus this thing times the integral of cosine of 2 theta. So I'll do that now. So this is actually just d theta here plus 18 times the integral from 0 to pi over 2 of cosine 2 theta d theta. So now the integral of 18 from 0 to, we'll just say the antiderivative of d theta is theta. So we're going to have 18 times theta from 0 to pi over 2. So it's going to be 18 times pi over 2 minus 0. So 18 times pi over 2 minus 0. And then we're going to have plus, and we have to do substitution, use substitution, or whatever variable you want to use. So we would have, the short answer is that this gives you, let's see, 1/2 cosine of u du. Yeah, we'll do it the long way, because then you would change your bounds normally too. So we'll go ahead and do that. So u equals 2 theta du equals 2 d theta, or 1/2 du equals d theta. So we'll have that 1/2. We can pull that to the outside, so that will give us 9. 18 divided by 2 is 9. Integral from, so here we had theta equals 0, theta equals pi over 2. For some reason I always have a hard time with this part. I know I usually don't do it when I actually work out the problems myself. I just do it at the end. But it should end up being 2 times theta. So here, so if you, I don't know how to say this right. So u equals 2 times theta. So here we have theta, here we have theta, well u equals 2 times theta, so we need to say that here we want u, so u equals 2 times 0, which is still 0. And then for the top one, we have u equals 2 times pi over 2. 2 times pi over 2 is pi. Cosine of u du. So we have area equals 18 divided by 2 is 9. 9 pi minus 0 plus, so I'll go ahead and kind of fill this in. So the antiderivative of cosine of u is sine of u, because the derivative of sine is cosine, so the sign doesn't change. So plus 9 sine of u evaluated from 0 to pi. If we go back to our circle over here, but imagine this is a unit circle now. It wasn't supposed to be before, but just imagine that this is a unit circle, because that's going to be when we're calculating sine and cosine, that's what you would have. I'm just not going to redraw the circle. So this point on a unit circle would be 1, 0. This point on a unit circle would be -1, 0. And the x value is cosine, the y value is sine. So sine of pi is this value here. It's 0. Sine of 0 is this value here. It is also 0. So we're going to have 0 minus 0, which is 0, times 9, which is 0. So this last half all evaluates to 0. So finally, the answer equals 9 pi, which is what we had established at the beginning, that 9 pi should be our answer. So this is how you can use the integral in the Cartesian coordinates to find the area of this entire circle. Now we're going to do the same steps, but with parametric coordinates. And let me try to find, go ahead and delete this here. I don't think we'll need any of that. And, oops. Okay, that's good enough. Alright, so that was using Cartesian coordinates. Now we can do the same thing using parametric coordinates. Once again, the equation, so we're still going to have our circle, and it's still going to be centered around the origin with the radius of 3, and our equation is 3 cosine of t and 3 sine of t. So for this one, we're going to do, I don't remember what alpha and beta stand for. I think, okay, so we can do it the same way. We can just find, this should work, if we just find the area of this right here. So then in that case, should be, alpha will be, I think it should be the t value that gives us this point here. And then beta will be the t values that gives us this point here. So this point in Cartesian space, which parametric equations still kind of use the same Cartesian space, it's just a different way of expressing the formula, whereas polar coordinates actually use a different space and a different way of expressing the formula. So here, this point is 0, 3. And this point is 3 is 0. So we want a t value that gives us, I hope I'm going the right direction. Maybe I want to go the other direction, actually. I think we want to start at this point and go at this point, because it depends on which direction our coordinate system is drawing the circle, whether it's drawing it this way or this way. This way. I didn't bother working that out ahead of time, but I'm going to guess that it's drawing it this way. So that's what we're going to go with. If anything, we should just end up with a wrong sign, the same value, but the wrong sign if I go backwards on my circle. So, okay, so what t value gives us 3, 0? So in that case, we want cosine of t to equal 1, and we want sine of t to equal 0. And that should be just 0, actually. Cosine of 0 is 1, and sine of 0 is 0. So we want 0. So area equals, we're going to set it up, as I said again, 4 times the integral from 0 to, and this should end up being, I think, pi over 2. Because for the second one, we want this to be 0, and we want this to be 1. So that we get 0 times 3 is 0. And 3 times 1 is 3. So pi over 2 would give us, well, it should give us this. So cosine of pi over 2, it would be actually the same point in space, so it would be 0. Yeah, so it's pi over 2. Because it's basically the same point in space, it's just that on the unit circle this would be a 1 instead of a 3, but otherwise it's the same value. It gives us the value back instead of a 0, and this one gives us back a 0. So 4 times integral from 0 to pi over 2 of g of t. So the thing to know here is that this side is g of t, should be correct, and this side is f of t. So the integral from 0 to pi over 2 of g of t, which is 3 sine of t, times the derivative of f of t. So that's going to be the derivative of 3 cosine of t. The derivative of 3 cosine of t should be negative 3 sine of t. Yes. Which probably means that I went the wrong direction on the circle, because I can already tell that we're going to end up with the wrong sign. I believe I should have went the other direction on my circle. Or maybe I mismatched the f of t and the g of t, but I think it goes this way, f of t and g of t. At any rate, it's still going to end up with, it'll end up with a negative 9 pi, so it's more or less still correct. Area equals 4. So we multiply 3 times negative 3, we get negative 9, we bring that to the outside. So actually we're going to end up with negative 36 times the integral from 0 to pi over 2 of sine squared t dt. And actually I erased that. I guess I still needed that. Where'd my pen go? This little chart up here. So we had sine squared theta plus cosine squared theta equals 1, or sine squared theta equals 1 minus cosine squared theta. That's what we're going to, sorry, that's not the one we wanted to use. We want power reducing. So that was sine squared theta equals 1/2 times 1 minus cosine squared theta. And actually, maybe I did go the right direction because we have a minus sign in there. I'm not 100% sure on that. So, yeah, so we're going to substitute that in, and this is supposed to be a 2 theta. Multitasking is not one of my strong points. That's not supposed to be squared. 1 minus cosine of 2 theta. Alright, now, so area equals negative 36 times the integral from 0 to pi over 2 of, and we have the 1/2, we can just bring that to the outside, so that'll be negative 36 divided by 2. 1 minus cosine 2 theta, and you can actually already see this basically looks like the last problem already, except I have the wrong sign because I think I went the wrong way around the circle. And that's not supposed to be a theta, that's supposed to be a t because I didn't switch the variables. And this is dt. Okay. A equals negative 18 times the integral from 0 to pi over 2 of dt minus the integral from, this would be 0 to pi over 2 cosine of 2t, that's supposed to be a t, dt, but I'm going to go ahead and do u substitution right now. So if u equals 2t, then 1/2 du equals dt. So this is going to be 1/2 cosine of u du, and we can change our bounds again. So 2 times 0 is 0, 2 times pi over 2 is pi. So area equals negative 18 times pi over 2 minus 0 minus 1/2 times the integral of cosine of u is negative sine u, and we're going from 0 to pi, and once again sine of 0 is 0 and sine of pi is 0, so this whole thing is going to evaluate to 0, and we're going to end up with area equals negative 9 pi, which is basically correct, except as I said, I made a mistake in the setup at the beginning so that we ended up with negative 9 instead of a positive 9. But anyway, you can see that it works, and it was actually a lot simpler than the other method. It didn't even involve trig substitution. It just was a little harder in the setup because conceptually you have to, either I'm making a simple mistake in that I'm mixing up the f of t and the g of t, which is possible, or once again you need to know which direction the curve flows in, and we could plot points and try to figure that out, but to be honest it's not worth it at this point. I think I've already illustrated the point clearly enough that for how to find the area using the parametric coordinate system. So yeah, we'll move on and do the polar coordinate system. Okay. So for the polar coordinate system, we have, once again, our circle. And the equation is r equals 3. The way of writing points is r theta, and the formula is up here. The integral from a to b of 1/2 f of theta squared d theta. So this one I did not even attempt to do ahead of time, so let's see if I can do this one. The integral from, so a to b, it's d theta, so this should be our first theta and our last theta. So this should be, we can try to do this one as the whole circle. I don't think it'll be a problem. So our first theta value right here is theta equals 0. As we move around the circle, the last theta value that we're concerned with is theta equals 2 pi. So we'll go from 0 to 2 pi. We don't need to multiply by anything because we're just going to try to do the entire circle. This is 1/2 times f of theta is r. So we can call this r squared d theta. So this one, as you can already see, is going to be a lot simpler than the other two. The integral from 0 to 2 pi of, what is r equal to? Well, r is equal to 3. It is always equal to 3. So r is equal to 3 or f of theta is equal to 3. They mean the same thing. So, yeah, so 3 squared is 9. 9 over 2, we can pull that to the outside. So we have 9 over 2. And then on the inside, the only thing we're left with is d theta. So we're going to have area equals 9 over 2 times theta. Let me use brackets here, actually. Evaluated from 0 to 2 pi, which is going to be 9 over 2 times 2 pi minus 0. Hey, look at that. The 2's cancel. Area equals 9 pi. So that was by far the simplest method for this particular problem for calculating for this particular shape, a circle. It was much easier in polar coordinates than either Cartesian or parametric. And to be honest, with this setup, it would be very easy just to find the regular formula that's memorized, area equals pi r squared, because this is already set up the way it is. So if we treat r as a constant, but integrate this without plugging in 3, we're going to have area equals 3, without plugging in 3, r squared over 2 times the integral from 0 to 2 pi d theta. Area equals r squared over 2 times theta, evaluated from 0 to 2 pi. Area equals r squared minus 2 times 2 pi minus 0. The 2's are going to cancel. We're going to get area equals r squared times pi, or pi r squared. So with this way, it was also very easy to deduce the formula. You can deduce the formula in the same steps with the other ones, but in this one, you didn't even have any other, how to say it, there was no other variables to confuse the r with. So yeah, there you go.